Hey there, folks. It's time for the third installment in my 6809 Playground Homebrew Computer series. Today I'm going to cover the circuit that generates the reset signal and also wire up a few other signals that are necessary to get the CPU to run some code. If you've been following along, well, welcome back. But if you're new here and not yet familiar with the background of this project, I've put a link to the introduction in the description below. Alrighty then, let's go. The reset signal performs a critical system function. It initializes anything that's watching it to a known state. In the case of the 6809, it also causes the CPU to fetch an address from a well-known location that's called the reset vector. It loads that value into the program counter and then begins executing code at that address. The reset signal on the 6809 is an active low signal. The CPU is then held in reset until the signal's rising edge, which then begins an 8-cycle process to bring the CPU out of reset and begin executing code. As you can see from the timing diagram, the reset signal only needs to be held low for a single cycle in order for the reset to take effect. Once it does, the CPU keeps repeating the address of the reset vector until the reset line goes high, and then again for the next 3 cycles, after which the bus status signal goes high, indicating a vector fetch, which then takes the next 2 cycles, followed by a dead cycle, followed by the fetch of the first instruction pointed to by the reset vector, which actually takes 2 cycles because the 6809 instruction fetch always fetches at least 2 bytes. So our job today is to do this right here. I'm going to be using this handy little IC from Dallas Semiconductor, the DS1813, to generate the reset signal. This part is connected to the 5-volt rail, ground, and an active low reset line using an open drain output. A comparator monitors VCC, and if VCC falls below a threshold voltage that's predefined based on the specific variant of the part you choose, the IC will then assert reset by pulling it low for approximately 150 milliseconds and then deassert it. It also monitors the reset line for an external pull down, like by a push button, and then it holds it low for 150 milliseconds after the external pull down releases it. As you can see from the block diagram, it even includes an internal pull-up resistor for the open drain output. It really couldn't be any easier to just integrate into a system. The application example in the datasheet basically shows you that you don't really need anything else in most circumstances. There is, however, this one sentence in the 6809E datasheet that gives me pause. 150 milliseconds is probably enough time for the clock generator to settle into its steady state. I mean, it really almost certainly is, but I can buy some cheap insurance with just a few additional components. So zooming in on the power-up timing diagram from the DS1813 datasheet, notice how the reset line is held low until VCC reaches the threshold voltage, after which the 150 millisecond reset period begins. Now, it's only this initial power-on reset that I want to delay. All the other resets, that are triggered by the push button or maybe even by software, those don't need any extra delay. I mean, the clock is definitely up and running when those events occur. So all I really need to do is delay the DS1813's VCC input reaching that threshold voltage, and that's really easy to do with just a simple RC circuit. So this right here, it ought to do the trick. A 3.3K resistor and a 100 microfarad capacitor, those have a time constant of about 1/3 of a second, and the current draw of the DS1813 is very low. The datasheet says, maximum of about 40 microamps. So the voltage drop across that resistor is going to be negligible. The diode that's in parallel with the resistor, that's there to provide a fast discharge path for the capacitor when the power is removed. So when the power is on, that diode will be reverse biased, so no current is going to flow. But when we switch the power off, the diode will become forward biased once the 5-volt rail drops. And at that point, the capacitor will then discharge much more quickly than it would have through the resistor alone. What I'm doing there is by adding that diode, I'm kind of giving that power on reset delay a fighting chance of working properly if you rapidly cycle the power. Now, recall that an RC time constant is the time it takes for the capacitor to charge to around 63% of the maximum voltage. So somewhere between 1.5 and 2 time constants will be required to charge the capacitor sufficiently to bring the CPU out of reset. So this means the power on reset delay is going to be roughly half a second, and that should be plenty of time for the clock to become stable. Okay, here's my little reset circuit built up on some free space on the clock module. Sorry, I know it's a little crowded in there, but this is breadboard land, so sorry, bear with me. So that white flying lead was just connected to my scope so I could verify the expected delays. So what I'm going to do here is now kind of switch to shaky cam and show you the circuit in action. Okay, here we are in my messy garage. That's also loud. And what we're going to do is we are going to watch the reset signals from the little reset circuit you see right down there. We zoom in. There we go. And we're going to watch those on my scope over here. Where is it? There it is. And I'm going to connect VCC, and VCC is going to be on channel 2, it's blue trace, and then the reset signal is the yellow trace on channel 1. So when I connect the power, here we go. We see a nice delay as VCC comes up. We can remove the power. I can do it again. Remove the power. And then we do it again. So we got a nice power on reset delay, which is pretty cool. And then I'm going to hit the reset button, and you can see the delay is much less. So hit the button there. Here I go, hit it, and then pops up a little later. All right, and that is the demo of the reset circuit. Okay, cool. We can generate a reset signal. Now let's take a look at some of the other signals that we need to hook up so that we can run some code on the CPU. First, let's look at the interrupt inputs. The 6809 has 3 of them: a non-maskable interrupt, an interrupt request, and a fast interrupt request. All 3 of these signals are active low, and they need to be pulled up to VCC. So I'm going to talk about interrupts in much more detail in a future video, but I am going to do something with NMI now, which I'm going to talk about in just a minute. Okay, moving on to the Hall input, it's also active low, and so we need to pull that up to VCC. And the tri-state control input, which when asserted basically disconnects the 6809 from the bus, that's active high, so we need to connect that to ground. Reset, we kind of know what we're doing with that already. And all the rest of the control signals are outputs, so we can kind of just let them flap in the breeze for now. Now, to run code on the CPU, all we really need to do is provide a valid instruction on the data bus. That way, when the CPU fetches an instruction, it will just fetch the one instruction that we hard code there, and it'll just keep executing that one instruction forever. The 6809 has a no-op instruction whose opcode is hexadecimal 12. And so we can just pull the data bus signals as shown here, and our CPU will then execute an endless stream of NOPs. While it does that, we can put the scope on some of the control outputs and the address bus to check for the activity that we'd expect to see. So before we do that, let me explain what I'm going to do with the NMI signal. So because the NMI is, it's non-maskable, it's actually a really handy way to, manually trigger something like the debugger or force the system back to the monitor environment, that sort of thing. So unlike the IRQ and FIRQ inputs, the NMI input is edge triggered, meaning that once it goes low and the NMI handler starts to run, the signal needs to go high again before the NMI can be triggered again. Now, normally if you're going to use a button to trigger, an event like this, you'll need to, to debounce it. Well, it turns out that the DS1813 is perfect for this application. It does exactly what I need. And so there's no need for any of the other sort of common debouncing techniques like an RC circuit plus a Schmidt trigger or something like that. So here's what we have so far. Here's the NMI circuit up there. And now the CPU should be all ready to run some code. A NOP is hard-coded on the data bus, and we can reset the CPU properly. So what we should see is the address bus just sort of counting upwards as it increments the program counter and fetches NOPs forever. So if I put the scope on A0, here what I see is that there's a pretty regular 250 kilohertz square wave. If the address bus were just counting up, what we would expect to see is basically the same trace on all the subsequent address lines, but at half their frequency each time I move up a bit. So here's A1, and it's counting at 125 kilohertz. And here's A2, and it's ticking away at 62.5 kilohertz. And that's really kind of just what we'd expect. All right, and finally, the LIC, or last instruction cycle signal. The 6809E raises this signal on the last cycle of every instruction. And since we have a 1 megahertz CPU clock, and each 6809 instruction takes a minimum of 2 cycles, we would expect an endless stream of NOPs to run the LIC at about 500 kilohertz, and that is in fact exactly what we see. So it looks to me like the CPU is in fact running an endless stream of NOPs. Okay, well now I need to think about hooking up some RAM and some ROM and maybe UART or something so the computer can actually do something useful. Before I can do any of that though, we need to be able to decode the addresses that the CPU puts out on the address bus. So I think the next installment is going to be all about that address decoder and then the other memory access signals that that need to be generated in order to read memory and things like that. So stay tuned for that. And thanks a lot for watching, and I hope to see you again soon.